The goal of this video is to introduce the COVID-19 polling place queue length model from the Stanford-MIT Healthy Elections Project. The goal of the tool is to add to a suite of line management tools by addressing a line that will form at a polling place under social distancing measures. Specifically, we imagine that very few voters will be allowed in the polling place room, and a secondary waiting room will need to hold a portion of the line. This tool answers a specific set of questions that we see here on the left. We can use this tool to estimate the outside queue capacity needs. We can estimate average wait times and estimate how many voters will wait too long. To start, let's walk through the picture on the right. The black rectangle is representative of the polling place room. Under our assumptions, we are limiting the capacity in this polling place room to 25 people in this case. Of the 25, we know a number of non-voters will be present. Election staff, observers, and security will take up some of this capacity. They're shown in the hollow red here. We have 4 election staff, 2 manning check-in, 2 manning the ballot scanner. We have 3 election observers and 2 security for a total of 9 non-voters. Next, some of this capacity will be taken up by voters who are in the process of voting. We assume that every distinct place that a voter can be in the voting process is full. Here we have 2 voters checking in, 4 voting booths, and 2 ballot scanners for a total of 8 voters in the voting process. The remaining capacity, in this case 8, is allocated to the inside queue, meaning that 8 future voters can wait in the polling place. The rest of the queue must wait in the secondary waiting area, outside the polling place room, either out of doors or just in a separate room. Let's take a look at the tables below to see how to input data into this tool. The upper table is for data input. To get started, click Add Polling Place to add a polling place to add a row to the table. We can add multiple rows, and we can use the orange trash can to delete rows. The Clear Data button in the bottom right will clear all of the rows, and we'll have to add another row. First, we select a bottleneck of the voting process from the drop-down menu. By default, it's the check-in step, but we can also select the voting booths or the ballot scanners. This won't change the underlying math, but will update the table headers. The bottleneck of your process is the step of the process which has the lowest throughput, calculated in voters per hour. And there are tooltips over both the bottleneck and some of the column headers to help guide you through the process. If you mouse away from those elements, the text will go away. We'll start with using a check-in process and put in some data. We'll assume that the room has the same setup as the picture we walked through above. Using that data, we'll put 25 people into the room capacity by clicking into the box and typing 25, or alternatively by using the up and down arrows. We had 9 non-voters in the room and 8 voter processing points. You'll notice that as we input data into these cells and click out of the cells, the table will automatically calculate the inside queue capacity. You'll notice here that it's 8, as it was up above. For the final inputs, let's consider a situation where there are 2 poll books at check-in for the polling place. Check-in takes 2 minutes per voter, and there are 54 voters per hour. The target wait time by default is 30 minutes, and we'll leave that alone for now. When we click Calculate, the results populate at the bottom. Farthest on the left, we see that voters wait on average about 8.5 minutes. The line is almost 8 people long on average, and of that, a little over 3 people are waiting outside on average. The polling place room is completely full 37% of the time, and there's a 3% chance that a voter will wait longer than our 30-minute target. This is the general protocol for studying a polling place using this tool. As a few final points, let's look at what numbers are valid inputs and what some of the alerts mean. As you hover over each unit in the input table, you'll see what number is allowed. For the room capacity, it needs to be a positive integer. No fractional numbers. For the number of non-voters in the room, it needs to be a non-negative integer, meaning that 0 is allowed, but it still must be an integer. For voter processing points and number of check-in stations, again, positive integers. And for the last 3 minutes, any positive number is allowed. Next, let's look at a few different cases to see what does and doesn't change as the inputs change. First, we'll add a scenario where there are 2 more non-voters and 2 fewer voter processing points. So we have the same room capacity, 2 more non-voters, and 2 fewer voter processing points, with the same number of check-in stations, average time, and arrival rate. You can see here that the results don't change at all. This is because the first 3 cells of input only feed into the model as a buildup for the inside queue capacity. That's an assumption that we make. Finally, we'll look at some alerts that the tool generates. To start, let's rename the polling places slow, medium, fast, and too fast. Any number or letter characters will work in the polling place names. We'll make these identical to above, but now we'll change the arrival rate. So here we'll have 56, 58, and 60. You'll notice that some alerts popped up. For the 56 and 58 voters per hour arrival rate, we have an orange alert. That means that the system is within 10% of its capacity limit, and small changes in the arrival rate, like I'm showing now, will cause the lines to grow very quickly. In the bottom case, the system is over capacity, and with the assumptions that we make in the model, we're not going to get good results, and the model will return an error. We'll delete this for now. When we calculate these polling places, you'll notice down below that even though we've only changed the voters per hour by 2 voters per hour in the 2 cases, because we're very close to the overall capacity of the system, average wait times grow very fast, as do the average total lengths of the queues and the chances that voters wait too long. Thanks very much for watching this video.